hundreds, maybe thousands of components. So wax is a component that become solid. And why they become solid? Because temperature, when we are producing from a reservoir, temperature decreases because reservoir temperature is high. When they come to surface, temperature is reduced. And this could be because of heat transfer to the environment, heat transfer, and component evaporating, and they need heat of evaporation. So that will result in the system become cooler. The pressure will decrease because we have pressure drop during production, so pressure also decreases. And then also composition can change because as we move up, when the pressure decreases, light component will come out of the oil phase, and that will increase the concentration of heavy component, and therefore the higher heavy component concentration, we can have more heavy component, and heavy component can result in wax formation. As I said, we have thousands of components. This is a different cut from an oil or different type of oil. And you see that you can have very light oily component, or you can have very heavy oily component that is dark fluid. So carbon number can be from methane, or up to, for heavy oil, can be 100. So in general, we can divide the hydrocarbon in different categories: paraffin, naphthalene, aromatic, and polar. Paraffin, they are either normal paraffin, that normal paraffin are a straight line, yeah, and we can have isoparaffin, they have a branch, or we can have naphthalene, they have a cyclic ring, they are naphthenes, okay? And then aromatic, I will discuss a bit later. And then we have resin and asphaltene, and I will discuss these later as well. So paraffin have a high boiling point. They have a their boiling point is high, or melting point is high, because they can get very close to each other, and the strength of that attraction is a function of how close they are with each other. And you can see here, C16 has a melting point of 17.8, C17 22.2. So you see that any component above C15, C17 and 18 can become solidified at ambient condition. Yeah, because ambient temperature may be 20 degrees. So you see that C17 can become solidified. But because they are not pure, their solidification, you have some light component, this is for pure component. So solidification would be, you know, a starting component that can result in wax formation is C18. This is a starting component for solidification. So in literature, we say that the solidification, that wax formation, any compound above C18 can form wax. And you can see that these compounds, they cannot get too close to each other because of the ring. And these branches, also because of branches, they cannot get, but paraffin, normal paraffin, they can get very close to each other, and therefore, because if they get very close to each other, the attraction between them will increase, and therefore they will solidify at higher temperature. And that's why in the literature, instead of saying, especially American, instead of saying wax problem, they say paraffin problem. So the wax is a solid phase of hydrocarbon, and normally temperature controls wax formation. But that is not always the case. As you remember, I said, if I can plot here, this is temperature. This is temperature. This is pressure. This is temperature. This is phase envelope. And this is wax phase boundary, like this. So below bubble point, as you increase temperature, more gas will dissolve in the oil. Therefore, wax appearance temperature shift to the left. Above bubble point, then when you apply pressure, the volume is reduced, and the hydrocarbon, when they freeze, their volume is decreased. So the wax phase boundary shift to the right. Higher the temperature, higher pressure, wax phase boundary shift to the right. Now, there was very interesting. So here is wax, risk of wax. There was a case that the operator was operating here. So outside wax phase boundary. But the reservoir pressure dropped, and as the reservoir pressure dropped, production rate is reduced. So what the operator did, reduce the separator pressure. When you reduce separator pressure, remember the pressure in the pipeline is a function of separator pressure. So if you reduce separator pressure, pipeline pressure will also drop and move inside wax phase boundary. And they basically used to have pigging operation every month to because it was a stratified flow. Do you know stratified flow? I think I explained to you. A stratified flow, at the bottom you have liquid, at the top you have gas. And here, a stratified flow, if the amount of liquid is small and the flow rate is not very high, that becomes a stratified flow. And they were injecting corrosion inhibitor to protect the pipeline against corrosion. And corrosion goes to the gas phase, and it was not protecting top of the pipeline, and therefore they have to they have to every month to do a batch inhibitor and corrosion inhibitor between 2 pigs. And then what happened, before they didn't have any wax problem, and they wanted to do that batch inhibitor, putting 2 pigs into the system, and it was a stormy weather, and they didn't do it for a month, and then temperature also dropped, so they went further inside the wax phase boundary, and then they wanted to do the pigging, and their pigs got stuck. And it was subsea pipeline, 40-kilometer pipeline block, and 18 kilometers pipeline block, and basically they have to replace the pipeline, and that's costing them around 50 million pounds. So you need to know this sort of potential problem. Okay, now can we give ourselves a 5 minutes break? So that resulted in also 5 months delay production. So wax can be a serious problem because hydrate, with reducing pressure, you can melt hydrate and open the pipeline. But wax doesn't respond to pressure normally, and more they respond to temperature. So the danger of wax blockage can be more than hydrate blockage. And it has a number of factors important. What we call it, the wax appearance temperature is important. And then wax deposition rate is important, because wax appearance increase the viscosity and make the fluid non-Newtonian, and wax deposition will reduce the diameter of the pipeline. And then we have what is called pour point. That is the point that the wax is solid and cannot move. There is another point of wax disappearance temperature that is useful for modeling wax. So there are various points that with respect to wax we need to consider. And this is a wax appearance and formation in a visual cell. Remember the cell I showed to you, this is the temperature probe. The test has been conducted in the same cell. So wax in crude oil produce a non-Newtonian fluid. Wax crystallization depends on degree of subcooling, how many degrees inside the wax phase boundary we are. That is an important factor. And wax crystallization in the crude can increase the result in high viscosity, high yield stress for restarting the flow. There are some pipeline in the world, if you stop flow, they get blockage. So you have to always follow that. Otherwise, you have a problem. And as I said, wax deposition reduces the diameter of the pipeline. One interesting point is that wax formation is an exothermic process. So wax normally deposit on the pipeline, internal pipeline wall. The main reason is that there is the coldest place, and they go there to lose the heat to the environment, and therefore they deposit there. Okay, and so if there is no temperature gradient, then there is no wax deposition. So wax would be in the system. Here you see that 10 to 6, we have wax deposition. If the oil temperature, wall temperature is 4, oil temperature is 8, less. And then if the wall temperature is 6, oil temperature is 6, and wax wall temperature is 4, very little. And if they are equal, there is no wax deposition. And if you look at in this figure, you see that the pipeline temperature initially is very high. This is Kelvin, so this is around 60 degrees initially. And then as the pipeline, the fluid move along the pipeline, it will reach to seabed temperature, which is around 8 degrees, 9 degrees, that is seabed temperature. So as you can imagine, when the pipeline, the fluid temperature reaches the seabed temperature, there is no drive for wax deposition. So you see that here, wax deposition has been reduced a lot. So initially, the beginning of the pipeline, because the temperature is above wax appearance temperature, there is no wax. But as we go along the pipeline, then you can have wax deposition. And wax deposition is not homogeneous. That is a point that maximum wax deposition happens. And then when the temperature reaches to ambient temperature, there is no wax deposition. Is that clear for you?
Yes, sir.
Okay. Yeah. So where wax deposit to reservoir formation, it might deposit there. Downhole equipment, because in reservoir, it can result in, because of Joule-Thomson effect in the reservoir, and maybe depending on where we are with respect to wax phase boundary, we can have the deposition of wax in the reservoir, downhole equipment, surface line, pipeline separator, and then a storage tank is a big problem. This wax deposition in the storage tank, because you can have a lot of wax produced as a small particle, and because its flow is happening, and they are, they are formed, but and suspended. When they reach a storage tank, then the gravity will work and they go to the bottom of the tank. And then we have wax problem at the bottom of the tank. So for decreased production rate is one of the outcome of wax deposition or formation, because deposition reduce the diameter, formation will change the friction, increase the friction, increase power requirement, and sometimes failures of the equipment. So normally we measure wax appearance temperature, And this is a lot depend that what technique you are using, and because the wax appearance temperature is not equilibrium point, like water freezing. Water freezing, we say melting point of water is 0, but formation of ice or freezing of water would be below 0. And sometimes it can be a lot below 0. Let's see if I can find my.
This is how cold it is.
Let's see if I can show it to you. The guy has gone to his granddad's house, and then let's see, glass of water, bottle of water. You can see now, am I right?
How cold it is in my dad's unheated house here in Glenshaw, Pittsburgh, Pennsylvania.
You see that the system is inside ice region.
Instant water crystallization.
Yeah,
Let's see.
it needs a nucleation, and here nucleation happens. Okay, so for any solid formation, you need to create a subcooling and nucleation for that to form solid. And that formation is exothermic, create heat. So wax formation also create heat. And then what we measure, wax appearance temperature, depend on many factors. Here, which factor played a role in this video? Mixing, yeah, shock. The system was inside wax appearance temperature and was not forming because needed nucleation. And when you move it, nucleation. Rate of cooling is another one. Presence of solid material is another one. Another factor is surface area available. So all of these will affect the wax appearance temperature. However, wax appearance temperature is not an equilibrium point. And you need crystallization and crystal growth. And a lot of potential needed to form a new phase. But so it depends on these factors that I mentioned to you. And we normally, for thermodynamic modeling, we use wax's appearance temperature. And wax disappearance temperature uh, is the temperature that all the wax particle will, once they form, uh, they are dissolved. It's like ice uh, melting point. That's by mistake or common error, we use it as ice formation point. Ice formation point is not zero. Ice melting is zero. There are various techniques for measuring uh, wax appearance temperature. Some of them are standards, but the most popular one is cross polarization microscopy. Yeah, this is the most popular one. If you look at PBT report, they use this technique. Um, we use quartz crystal microbalance, which is, is more accurate than this technique. But lab, if you go commercial lab, they are more familiar with this one. But there are other techniques, laser-based solid detection, viscometry, we measure viscosity, and when the wax appear, viscosity increase, differential scanning colorimetry, in that wax formation exothermic, so we measure the heat release uh, upon wax formation and heat absorbed during wax melting and find the wax appearance and disappearance. But because you need to have a high rate of rate of cooling and heating, then the results are not very accurate. And then we have ASTM, American Standard for Testing Material. ASTM, they use cloud point and they put the sample in a graduated visual cell and they cool it and then they look at whether the wax is formed. You can see that is not very useful for transparent fluid. So this is wax measurement, and you see that this is cross-polar microscopy, CPM, and here you don't see any wax. And for those of you who have a sharp eye, there is here some wax here, but this is completely now, we know that this is wax, wax formation. And here, this is wax formation, definitely. The other factor is wax deposition. Now, wax formation increases the viscosity. Wax deposition is reduce the pipeline diameter. So here, what is called cold finger. This is the waxy oil, and they pass this U-tube here, and the cold fluid goes through this U-tube. And after a certain amount of time, this is a mixer at the bottom, and they measure the amount of wax deposited there. You can see that this is the deposition and inhibitor, when you don't have inhibitor, and this is with inhibitor. So this sort of test is again very popular, but the weak point of this technique is that normally you have high driving force. Normally the oil is at 40 degrees, and then the cold finger is at 4 degrees. Second point is not under pressure. It's atmospheric condition. You cannot take into account the effect of gases. The other point is that it's destructive test. After the test, you have to use another sample, and sample is very expensive. And you need a lot of sample. You need half a liter, 250 cc. So you need a lot of, and then you don't have efficient mixing. You don't have the mixing. You don't have the shear. The fluid moving the pipeline creates shear on the wax deposited on the pipeline. So there has a lot of weak point, and and this is a coal finger, our coal finger facilities that we use it for an oil from Turkmenistan, and this is effect of shear on the wax deposition. This case was very interesting. The vendor said that you have to use 1,200 ppm of wax inhibitor, and we demonstrated that if there is a small shear, there will be no deposition. And a small shear, and during a startup and shutdown, shear can be very small, but then after the choke, shear is a lot. So we simulate all the condition, and we say to them that you don't need any inhibitor. What is extra we did, we have a new setup that we can rotate the wall, and then when we rotate the wall, we can create that shear force. So this is another one that we can basically have a coarse crystal microbalance. This is a QCM, and this is a mixer. We have now improved this further. The good point here is that the amount of sample you need around 30 cc, and after the test you can recover it. So here, cold fluid comes here, and the oil is adjusted here, temperature, and we can simulate different gradients. And this is some of the result. You can see that this is dead oil. You see that as the pressure increases, wax appearance temperature move to the right. And then this is wax appearance temperature for a live oil, and this is wax disappearance temperature. As I said, this is a real test result. As you increase temperature, you increase the amount of light component in the oil. Wax phase boundary shift to the left, and then above bubble point, wax phase boundary shift to the right. And this is QCM result, coarse crystal microbalance. This is wax appearance, this is wax disappearance. And you can see there can be quite a large difference between them. And this is effect of inhibitor. You can see that inhibitor prevent, this is without inhibitor, that we have to flow at above 30 degrees to make sure that we don't have wax blockage, wax formation. Even if you want to be more accurate, then you need to increase to 37 degrees. But obviously that will be expensive, but you can use inhibitor, and you see that then you can operate at 20 degrees without wax problem. This is another inhibitor that reduces wax deposition. You see that here, the point of wax appearance and disappearance doesn't change, but the amount of deposition changes. so less wax stick to the wall. And this is further investigation, temperature difference, wall temperature difference. And you see that the more the difference is, the temperature of this oil is at 20 degrees. So if you have wall temperature 20 degrees, so that 20 degrees difference, maximum wax deposition. If you reduce it, then more and more um, reduction in wax deposition. And we also can test the effect of different inhibitors. And one interesting point is that wax inhibitor, they have an optimum point. They have a critical point. And you see that for this inhibitor and the amount of inhibitor, um, you see that the increasing the amount of inhibitor here is 100 ppm is enough. For this one, maybe 120 ppm is enough. You see that above that doesn't have any effect. You're just wasting your money. Doesn't have any effect on the result. Wax control, how we control wax deposition. If the wax is inside the well bore, we can use gauge cutter. Do you remember gauge cutter? Yeah, or wire line baler. Do you remember that? It was it was last week. And in the pipeline, you can use pig, or this is the most technique, popular technique. Thermal point. Thermal point is using hot oiling and or electrical heating or hot water injection. And there is another technique based on chemical reaction. They have two reactants, they work together and produce heat. Chemical method, solvent, wax crystal modifier, wax dispersants, and some people have reported microbial treatment or magnetic treatment. So combination of these can